Usually when you talk about making a massive investment in your home, say, um, renovating a kitchen or putting in a pool, there is this expectation of permanence,
Right. Yeah.
like security. You
Yeah.
put the money in, the concrete dries, and it's just there. It works. You don't micromanage it.
Exactly. It's a fixed asset.
But then you look at what's happening right now with home energy systems, specifically residential solar and these massive lithium-ion battery setups. And it is, frankly, a completely different story.
Oh, entirely. It's a totally different beast.
I mean, imagine going out and buying a high-end luxury sports car. Let's say a pristine, like R250,000 vehicle.
Okay.
You park it in your driveway, but every single night, you deliberately leave the keys in the ignition. You leave the engine running, the headlights glaring, just, waiting for anyone to come along and completely drain the battery.
Yeah, you'd never do that.
It sounds absurd. No one would do that.
It's the definition of reckless. I mean, you're taking a highly volatile, highly expensive chemical and financial asset and leaving it entirely unprotected from the environment it operates within.
And yet, according to the sources we are unpacking today, that is precisely what hundreds of thousands of homeowners are doing right now
Every single day.
with their incredibly expensive solar and battery systems. So welcome to the deep dive. Today our mission is to completely crack the code on a stack of technical schematics, software release notes, and some really fascinating financial return on investment models.
Yeah, the numbers on this are wild.
They really are. And this is all regarding something called the SolarBoost Complete Home Energy Management Platform. We're going to explore how adding what their engineers call an intelligence layer to a home physically protects these massive investments during load shedding.
Right, because right now they're very vulnerable.
Exactly. We're going to look at how it automates away that exhausting daily cognitive load of managing your power, and really how it fundamentally transforms the daily life of a typical South African household.
What we are really tracking here, for you listening, is a paradigm shift in residential infrastructure.
Paradigm shift. Okay. Unpack that.
Well, it's the transition from a passive energy system to an active, optimizing ecosystem. For a long time, the dominant narrative in the solar industry has just been buy some photovoltaic panels, buy a lithium iron phosphate battery, slap a hybrid inverter on the wall, and boom.
Boom. You're safe from the grid.
Right, you're off the grid, you're safe. But as this technical documentation clearly outlines, a standard solar and battery setup is fundamentally passive.
Passive, meaning it just sits there.
It just sits there.
Yeah.
It does exactly what it is told by whatever appliance demands power. If the national grid drops and your 3-kilowatt geyser asks for power, the battery just blindly supplies it
Wow.
until the battery physically dies. The SolarBoost platform steps in as an active manager. It's a localized, high-speed computational brain that sits right between your delicate hardware and the absolute chaos of the power grid.
Let's start right there, actually, with that chaos.
Right.
Because before we can even begin to understand the incredibly cool technical solutions SolarBoost has engineered, and we are going to get deep into the physics today.
Oh, yeah, the microarchitecture is fascinating.
It really is. But we have to establish the specific, costly problems this technology was built to solve first. Like, you can't appreciate the tourniquet until you understand the bleeding, right?
That's a great way to put it.
And these documents explicitly identify a compounding, basically a perfect storm of energy challenges currently facing homeowners right now.
It is a multifaceted crisis. First, obviously, you have relentless load shedding, which isn't just an inconvenience anymore.
Now it's daily life.
Right. But technically speaking, it fundamentally disrupts the thermal and electrical equilibrium of a home. It's constantly threatening the health of any connected hardware.
Okay, that's phase one of the storm.
Second, you have the severe financial pressure. We are looking at compounding electricity tariff increases of 15% or more annually.
Which is just unsustainable for most people.
It's a geometric progression that destroys household budgets. And then third, to escape those first two problems, homeowners are taking on massive capital expenditure.
Right, the solar setups.
Yeah. They are spending anywhere from R80,000 to R250,000, sometimes much more, to build these microgrids in their garages.
So you spend the R150,000. You think, great, I am off the grid, I am safe from load shedding, I can finally just relax and watch TV.
But you're not safe.
Exactly.
All right.
The release notes highlight a massive invisible danger here. Deep battery discharge cycles during extended outages.
This is the critical vulnerability.
The engineers state emphatically that these deep discharges degrade incredibly expensive equipment. I want to spend some time here, actually,
Sure.
because people, myself included, treat batteries like they're just um, buckets of electricity.
Right, a bucket.
You pour the electricity in, you pour it out. Simple. But that's not what's happening at all, is it? Explain the actual chemistry to us. Why is a deep discharge so lethal to the health of a lithium-ion battery?
To understand the vulnerability, we really have to look at the micro level of lithium-ion chemistry. A battery is not a bucket. It is a highly volatile, strictly controlled chemical environment.
Okay.
Inside those cells, you have an anode, typically made of graphite, and a cathode, usually a lithium metal oxide.
Graphite and lithium metal oxide, got it.
When you charge the battery, lithium ions are physically forced to travel through a liquid electrolyte, and they wedge themselves into the microscopic crystalline structure of the graphite anode.
Oh, wow. So they were literally cramming themselves into the physical spaces between the graphite layers.
Yes, the technical term is intercalation.
Intercalation.
Right. And when you draw power from the battery, those ions travel back to the cathode. Now, here is where the damage occurs. When you drain a lithium-ion battery, deeply taking the state of charge, or SOC, down to 0, 5, or even 10%, you are extracting almost all of those lithium ions out of the anode.
Which leaves it empty.
Yes, and this causes the physical structure of the graphite to contract significantly.
Oh, it physically shrinks.
It shrinks. Then, when the power comes back on and the system rushes to recharge, the graphite expands rapidly as the ions just flood back in.
So it's swelling and shrinking.
Exactly. This constant extreme expansion and contraction causes microscopic physical fractures in the electrode structures.
It's mechanical stress, like
Right.
bending a piece of metal back and forth until it snaps.
Exactly that kind of fatigue. Furthermore, at very low voltages, the chemical stability of the liquid electrolyte breaks down. The protective layer on the anode, which is called the solid electrolyte interface, or SEI layer, starts to crack and dissolve.
And I'm guessing that's bad.
Very bad. The battery has to consume more of its own internal active lithium to rebuild that layer, which means that lithium is no longer available to store energy. Your total capacity permanently shrinks.
That's terrifying for a R150,000 asset.
And doing this once or twice might not show immediate catastrophic damage, but doing it consistently, imagine a prolonged stage 6 load shedding scenario.
Okay, let's play that out.
The grid is down for 4 hours. It's a cold evening. Your battery is constantly fighting to keep heavy appliances, heaters, ovens, geysers running without any grid support.
Right.
It drains down to 2%. Then the grid comes back for 2 hours, slams the battery with a high current charge, and then the grid drops again.
Yeah.
That extreme cycling under high thermal stress is how you permanently destroy the chemical lifespan of the battery. You take an asset engineered to last 10 years and 10,000 cycles, and you basically kill it in 3 years.
Returning to that analogy of the sports car earlier, it really is like redlining the engine in first gear every single time you drive.
Yes.
The engine block gets incredibly hot, the oil breaks down, and eventually the pistons just fuse together.
And in a standard passive setup, the battery has absolutely no way of defending itself. None.
Because it's a bucket.
Right. It cannot communicate with your house. It can't tell the geyser to stop pulling 3 kilowatts of power. It just gives and gives until the internal battery management system, the BMS, recognizes a critical voltage drop and forcefully severs the connection.
Just to stop it from catching fire, basically.
Exactly. To prevent a thermal runaway event or total localized cell failure. But by the time that hard emergency shutdown happens, the long-term chemical degradation has already been locked in. You've already done the damage.
Okay, I have to push back on this, though, just playing the role of the consumer for a second.
Sure.
If I go to an installer today and buy a top-of-the-line, name-brand hybrid inverter, the marketing material is definitely going to tell me it's a smart inverter.
Oh, absolutely it will.
Don't these solar systems already have intelligence built in? Like, I have an app on my phone where I can see the power flowing in real time. Doesn't the inverter protect the battery?
That is probably the single most common and most expensive misconception in the entire solar industry right now.
Wait, really?
Yes, modern inverters have microprocessors and built-in logic, sure, but it is a highly localized, deeply limited form of intelligence. An inverter is essentially just a gateway and a converter.
A gateway.
Its primary job is to manage the flow of direct current, DC, from the solar panels, convert it to alternating current, AC, for the house to use, and push DC power into or out of the battery.
So it's a traffic cop for electricity.
Exactly. It is exceptionally good at routing power, but what the SolarBoost white papers make very clear is the vast difference between an inverter and an active optimization platform.
It lacks context.
It completely lacks situational awareness. Your quote-unquote smart inverter does not know that it is Tuesday evening and you are about to start cooking dinner.
Right.
It does not know that the municipal grid just failed unexpectedly. It certainly does not know that your pool pump, which is wired on an entirely different circuit breaker 50 meters away, just clicked on via a dumb mechanical timer.
It's trying to pull a massive load.
Right, trying to pull 750 watts of power. The inverter just sees an aggregate demand for alternating current on the main line, and it blindly supplies that power from the battery. It has no idea what it is powering, only that power is being requested.
Which brings us to the manual burden, the human element of this crisis. The sources paint a very vivid picture of the daily reality. For a lot of people listening to this right now,
The running around.
you get the push notification on your phone that load shedding is starting in 10 minutes. Or worse, the power just drops without warning.
Which happens all the time.
Suddenly, you are running around the house like a madman. You are physically flipping breakers on the distribution board to isolate the heavy loads.
Yeah.
You are constantly refreshing your inverter app to see if the battery is draining too fast.
Yep.
You are yelling at the kids to turn off the PlayStation. You are standing outside in the dark trying to figure out if the borehole pump is running. You spent all this money to buy peace of mind.
And
Instead, you bought yourself a highly stressful part-time job as a manual power grid manager.
it is an immense cognitive load. And the SolarBoost vision statement addresses this directly. Their goal was to completely eliminate the manual management of circuits and appliances.
Because humans are terrible at it.
We are. They recognized that relying on human intervention to protect a R150,000 chemical asset during highly unpredictable municipal grid failures is just a fundamentally flawed, unsustainable strategy.
Yeah, we forget to check the app. We fall asleep.
We get stuck in traffic on the way home from work.
Exactly. And if you fall asleep and that mechanical timer turns your pool pump on at 2 a.m. during a blackout, it drains your battery to zero while you are dreaming.
Yes.
You wake up in the dark, your fridge is defrosting, your alarm system is dead, and you just shaved months off the chemical lifespan of your lithium cells.
It's a disaster scenario.
Yeah, so that is the threat. That is the glaring vulnerability of this so-called smart home. Now, let's get into the mechanics of how this SolarBoost system actually solves it. Because before the system can execute any kind of protection protocol, it has to actually know that the grid is collapsing.
Right. Detection is step one.
And this is where the hardware architecture gets genuinely fascinating. The schematics introduce the central intelligence hub of the platform, which they call the GridGuard Master Controller.
The hardware design here is incredible. Industrial grade. The GridGuard is not relying on a cheap, off-the-shelf smart home hub.
No Raspberry Pi here.
No. It is powered by an ESP32 dual-core microprocessor. For the software engineers listening, the ESP32 is a highly reliable, low-power system on a chip that is ubiquitous in industrial Internet of Things applications.
That's robust.
Very. And crucially, it is running a real-time operating system, or RTOS.
RTOS. What does that mean for the average user?
This means it is capable of processing complex, localized logic and executing hardware interrupts in a matter of milliseconds, without ever needing to ping a cloud server to ask for permission.
Because if the grid is down, the internet might be down.
Exactly.
So cloud reliance is a death sentence for a protection system.
Absolutely. If it has to wait for an AWS server to tell it to turn off the pool pump, it's already too late. The GridGuard controller is hardwired directly into the home's primary electrical distribution board. It features extensive multi-sensor integration. We are talking about inputs for up to 12 CT clamps to measure precise current flow across different phases, ambient and contact temperature probes, and highly sensitive voltage monitoring circuits.
But the absolute crown jewel of its capability, and this is the specific feature that PowerPulse Innovations, the parent company, has patented, is its preemptive load shedding detection mechanism.
Yes, the 49.8 hertz trigger.
I was reading the technical breakdown of this mechanism, and it is brilliant. It doesn't just wait for the power to snap off and the lights to go dark. It continuously monitors the physical frequency of the incoming grid power,
Continuously.
and it triggers an automated lockdown response the moment that frequency dips below 49.8 hertz.
Yeah.
I need to understand the physics of this. Why 49.8 hertz?
Okay, to understand this trigger, we have to look at how alternating current is generated on a massive national scale.
Okay, let's zoom out to ESCOM.
Right. In South Africa, Eskom operates enormous power stations, primarily coal-fired. Inside those stations, massive physical turbines are spinning.
Giant magnets, essentially.
Exactly. They are calibrated to spin at a highly precise speed to generate an electrical wave that reverses direction exactly 50 times per second.
50 times a second.
That is your 50 hertz frequency. That 50 hertz hum is the literal physical heartbeat of the entire national electrical grid.
So every plug point in the country is pulsing at that exact rhythm.
Yes, from Cape Town to Musina. Now, the grid relies on a delicate, constant balance between generation, the power the turbines are pushing out, and load, the power that every house, factory, and mine is pulling in.
Right, supply and demand.
What happens when there is a sudden spike in demand or a sudden loss of generation, meaning the load exceeds the supply? Think of it like riding a bicycle on a flat road.
Yeah.
And suddenly you hit a steep incline. The incline represents the increased electrical demand. If you don't instantly pedal harder, representing the power station injecting more steam to spin the turbine faster, the physical resistance causes your pedaling to slow down.
So the physical drag actually slows the spinning magnets inside the generator.
It creates immense electromagnetic drag on the colossal rotors at the power station. When the national grid bogs down because demand is exceeding supply, those massive physical turbines physically slow their rotation.
Wow.
Consequently, the frequency of the electrical current rippling across the entire country drops below 50 hertz.
Which is dangerous.
Extremely. Eskom implements load shedding, deliberately cutting off entire cities or neighborhoods specifically to artificially reduce that load, removing the steep incline so the turbines can speed back up to 50 hertz and prevent the entire national grid from experiencing a catastrophic cascading collapse.
So the ESP32 in the grid guard is sitting in my garage, basically constantly measuring the distance between those sine waves.
Yes.
And when it detects a microfluctuation, specifically a drop to 49.8 hertz, it knows with absolute mathematical certainty that the grid is critically unstable and a local blackout is imminent.
It knows before the lights go out.
But I'm looking at this and thinking, why go through the immense engineering effort of building custom silicon and writing RTOS code to measure microfluctuations in a physical AC sine wave?
It seems like overkill.
Right. Why not just write a simple script that pulls a schedule from one of those load-shedding apps we all have on our phones? Can't the system just ping an API and say, oh, the schedule says it's 4:00 p.m., time to shut down the pool pump?
On paper, an API integration sounds easier. Definitely. But when you look at the physical reality of the South African power distribution network, relying on a digital schedule is incredibly dangerous for a hardware protection system.
Because they're inaccurate.
Schedules are theoretical. The grid is physical. Schedules change at a moment's notice. You might be scheduled for stage 2, but a boiler tube bursts at a power station, and within 3 minutes, the entire country is escalated to stage 4.
Right, the app hasn't updated yet.
Or consider municipal switching. The app schedule says your power goes off at 4:00 p.m., but the guy at the local municipal substation actually flips the physical switch at 4:17 p.m.
Oh, I see the problem. If my smart home system dutifully shuts down my geyser, my oven, and my pool pump based on an app schedule at 4:00 p.m., but the grid power is actually still flowing until 4:17, I am needlessly sitting in the dark.
Wasting 17 minutes of free grid or solar power.
Exactly.
And the inverse is even worse. If a local transformer blows or a cable is stolen outside of your scheduled load-shedding window, an app-based system is completely blind.
Because the API says everything is fine.
Right. The grid vanishes unexpectedly, your heavy appliances instantly start draining the battery at maximum capacity, and the system has no idea it's supposed to be protecting the battery.
So the app is a proxy, but the frequency is the truth.
Exactly. By measuring the physical physics of the copper wire coming into the house, that real-time 49.8 hertz hardware trigger the SolarBoost system reacts with localized, infallible accuracy. It doesn't guess based on a database. It knows based on physics.
It's feeling the pulse.
And because that frequency drag happens across the network before the local substation breakers actually trip, the RTOS can process the interrupt and execute a lockdown command to the house in milliseconds, bracing the entire electrical system for impact before the blackout actually hits.
I love that concept of braces for impacts. Like this system feels the microscopic tremors of the earthquake a split second before the ground actually opens up.
That's a great analogy.
And it slams all the bulkheads shut to protect the ship. But to slam those bulkheads shut, it has to communicate with the rest of the house.
Right, it has to send the signal.
And the engineering documents specify they use something called LoRa mesh networking for whole home coverage. Why are we introducing a proprietary radio network? Why not just connect the relays and sensors to the home's existing Wi-Fi router? Everything else in my house uses Wi-Fi.
Wi-Fi is fantastic for streaming high bandwidth data like Netflix, but it is notoriously terrible for mission-critical industrial control.
Really?
Primarily due to the physics of RF wave propagation. Wi-Fi operates on a 2.4 gigahertz or 5 gigahertz frequency. These are very short, high-energy wavelengths. Now, consider how South African homes are constructed.
Brick and mortar.
Exactly. They are almost universally built with thick, double-layer brick, mortar, and concrete slabs. Bricks and mortar contain trace amounts of moisture.
Yep.
2.4 gigahertz is, not coincidentally, the exact frequency that microwave ovens use to excite water molecules and generate heat.
Wait, really? Oh, wow. So the water in the brick wall is literally absorbing the Wi-Fi signal.
Exactly. The radio energy is absorbed and dissipated as microscopic heat within the wall.
That is mind-blowing.
This is why your Wi-Fi signal drops dramatically when you walk to the far side of your house or out to the garden where the pool pump is located.
The bricks are microwaving the signal.
Basically, yes. Now, imagine a blackout scenario. The grid drops. The grid guard controller urgently needs to send a signal to shut off the pool pump relay to save the battery. But the house Wi-Fi router is currently rebooting because it just switched over from grid to inverter power.
Oh, because the router loses power for a second.
Right. Or the signal simply cannot punch through 3 external brick walls. The command drops, the pool pump keeps running, and the battery dies. Relying on Wi-Fi for critical protection is a single point of failure.
So how does LoRa solve the physics problem?
LoRa stands for long-range radio. It operates on a sub-gigahertz frequency band, specifically 900 megahertz in this region.
Lower frequency.
Because the wavelength is significantly longer and operates at a lower frequency, it doesn't get absorbed by moisture in the same way. The waves can physically bend around obstacles and penetrate dense concrete and brick with incredible efficiency.
How far can it reach?
The technical specifications note that the SolarBoost LoRa transmitters have a clear line of sight range of over 2 kilometers.
2 kilometers.
Yes. Even through multiple brick walls, communicating across a large residential property is trivial. Furthermore, it doesn't use a hub-and-spoke model like a Wi-Fi router. It operates as a mesh network.
Meaning the devices talk directly to each other?
Yes. Every single smart relay installed in the house acts as a repeater. If the master controller in the garage sends a signal to the borehole pump at the far end of the garden, the signal bounces from the garage to the kitchen relay to the bedroom relay and out to the pump.
So it finds its own path.
It creates a highly resilient, self-healing web of communication that operates entirely independently of your internet router.
So we have this bulletproof sub-gigahertz communication network wrapping the house. And we have this hyper-fast ESP32 brain monitoring the 50 hertz heartbeat at the national grid.
Yeah.
Let's walk through the exact sequence of events.
Okay, let's run a simulation.
The power station turbine bogs down. The heartbeat drops to 49.8 hertz. The grid guard detects the interrupt, bypasses its normal operating loop, and screams, "Brace for impact!" over the LoRa mesh network.
Right.
What is the actual triage process? How does the house physically brace itself? Because this is the core of the platform's value proposition, the 3-stage battery protection protocol.
To understand the triage, we have to look closely at Dashboard 5 in the software layer, which is entirely dedicated to configuring the battery protection system.
Okay, Dashboard 5.
The core algorithmic philosophy here is that not all power consumption is equal. And as the chemical reserves of the battery deplete, the system's logic needs to become increasingly defensive, hostile even, to non-essential loads.
Hostile, I like that.
To execute this, SolarBoost relies on 4 highly configurable thresholds based on the battery's real-time state of charge, or SOC.
Let's break down these thresholds, because this logic is what elevates the system from a series of dumb remote control switches into an actual active optimization platform.
The first and highest threshold is the minimum SOC, which the system defaults to 30%. The second is the critical SOC, defaulting to 20%. The third is the emergency reserve, sitting at 10%.
30, 20, 10. Simple enough.
And finally, there is a hard deck. The max depth of discharge setting, typically configured at 90%. which governs the absolute floor to optimize the lithium chemistry's lifespan, meaning the battery never drops below 10% actual capacity.
Got it.
Based on these dynamic thresholds, the system executes a cascading three-stage load shedding plan.
Okay, let's run that simulation. The grid frequency drops, the power cuts, it's early evening, and the lithium battery is sitting comfortably at 80% charge. What is the system doing at this precise moment?
At 80% SOC, the system's logic is relaxed. The grid guard knows you are off-grid, but the battery has plenty of stored energy. The bulkheads are open.
I can watch TV.
You can run your LED lights, watch television, use the microwave, run the fridge. The inverter is happily pulling power from the battery.
Life is good.
But let's say this isn't a quick 2-hour outage. A substation blew up and you are facing a 6-hour blackout.
A very realistic scenario.
The hours tick by. The battery slowly, steadily drains. It hits 50%. It hits 40%. The system is monitoring, but nothing changes yet. But then, the telemetry data reports the battery has hit that first threshold, 30% SOC.
Ah.
The RTOS immediately triggers stage 1 of the load shedding plan.
The first line of defense. Sealing the outer bulkheads.
Precisely. At stage 1, the grid guard fires commands across the LoRa mesh to automatically disable all non-essential heavy-draw appliance relays.
Like what?
According to the deployment examples in the manual, this immediately severs power to circuits like the pool pump, the borehole pump, maybe the underfloor heating.
Makes sense.
These are lifestyle appliances. They are nice to have running, but their utility is absolutely not worth the chemical degradation they will cause to the battery if left running late into the night.
Right, the pool water can sit stagnant for a few hours. It can wait until tomorrow when the solar panels are generating free power again.
Exactly.
But the outage continues. The grid is still dead, we're deep into the night, and the battery continues to drop. It hits 20%.
Now the system enters stage 2, critical SOC. The triage logic becomes much more aggressive. It looks at the heavy thermal loads.
Things generating heat.
Right. It immediately forces the geyser relay into a strict solar-only mode, meaning the geyser is mathematically blocked from drawing even a single watt of power from the battery.
Wow, okay.
It will forcefully disable heavy indoor appliances like the electric oven or tumble dryer. It alters the priority queue for the stove. The system is now actively hoarding the remaining 20% of the battery's chemical energy.
It's panicking a little bit.
It is reserving it strictly for the preservation of your most vital circuits, your interior lighting, your refrigeration so your food doesn't spoil, and your security systems.
But the crisis isn't over. It's 3 a.m. The battery creeps down to 10%.
Stage 3, emergency reserve. The system executes a massive load strip.
A load strip.
Every single relay in the house, except for those specifically tagged as lifeline circuits, is severed. The house goes into absolute survival mode.
Just the bare minimum.
Typically, this leaves only a few strategic LED lights, the kitchen fridge, and the Wi-Fi modem powered on. Simultaneously, the grid guard uses its cellular backup or remaining internet connection to fire off an emergency push notification to the homeowner's phone,
Alerting them.
alerting them that the house has entered stage 3 and critical power failure is imminent if consumption isn't manually halted.
If we stick with the ship's captain metaphor from earlier, the hull is breached. The captain has sealed all the outer compartments, shut down the secondary engines, and is now diverting all remaining auxiliary power strictly to life support and the radio transmitter.
That is the exact operational logic.
It is a ruthless, automated triage system. The pool pump is a flooded compartment. The oven is a flooded compartment. It isolates them to ensure the vital organs of the house stay alive.
And if we take this technical chemical preservation process and extrapolate it directly into financial terms via the ROI models provided, the economic impact is staggering.
Well, let's talk about the money.
By ruthlessly enforcing these SOC boundaries, by literally physically preventing the inverter from dragging the lithium cells down to 2% or 0% during every single extended outage, the SolarBoost system drastically alters the chemical degradation curve we discussed earlier.
It stops the mechanical stress on the graphite.
It prevents those microfractures in the anode. The documentation states that this automated protection protocol extends a standard R150,000 battery's lifespan from roughly 5 years under heavy, unprotected South African load-shedding conditions to over 10 years of viable service.
Let's do the actual accounting on that, because doubling the lifespan of a six-figure asset is not a minor footnote. That is massive capital preservation.
The math is very straightforward. If you purchase a 150,000 lithium battery bank and it only lasts 5 years because you are constantly deep discharging it during stage 6 load shedding, that asset is effectively depreciating at a rate of R30,000 every single year.
R30,000 a year, just gone.
That breaks down to R2500 of invisible value vanishing from your garage every single month.
Wow, R2500 a month. You don't see it, but it's bleeding out.
Exactly. By doubling the lifespan to 10 years using the 3-stage hardware protection protocol, your annual depreciation drops to R15,000. Your monthly depreciation drops to R12,250.
So you are literally keeping R1250 a month on your personal balance sheet.
Avoiding invisible chemical degradation costs. Simply by having an automated electrical controller that knows exactly when to sever the connection to the pool pump and the geyser.
It is brilliant because it removes the human error. You don't have to think about the degradation curve. The ESP32 thinks about it for you thousands of times a second.
Exactly.
But this raises a deep mechanical question for me.
Sure.
We know when things get turned off, the logic thresholds of the 3-stage triage. But how does the system physically control these heavy appliances?
The relays.
Right. If the grid guard brain is bolted to the wall in the garage next to the inverter, how is it physically stopping the pool pump motor from spinning or the stove element from heating up without a human being running to the distribution board and manually pulling the physical breaker switch down?
This is achieved through the physical integration of the smart relay network. We discussed the sub-gigahertz LoRa communication earlier, but the actual physical interruption of the electrical current happens via these smart relays.
Okay, so what do they look like?
A standard residential installation involves retrofitting 6 to 12 of these relays directly into the home's main distribution board, typically mounted on the DI rail right next to the existing circuit breakers.
And these aren't just like tiny little smart switches you plug into a wall socket, right?
Not at all. These are industrial-grade, solid-state, or heavy-duty mechanical contactors. They are capable of safely switching up to 30 amps of alternating current under full load.
That's a lot of power.
But their most critical feature is the integration of CT clamps, or current transformers.
I see those mentioned constantly in the schematics. 12 CT clamp inputs. Unpack that jargon for us. What is a CT clamp and how does it read power?
A current transformer clamp is essentially a hinged magnetic ring. The installer opens the ring and clips it entirely around the insulated copper wire feeding a specific circuit, say, the wire going to the oven.
So they don't have to strip the wire.
No, it does not require cutting the wire or splicing into the copper, which makes it very safe.
Oh, that's smart.
Now, according to Ampere's law, any wire carrying an alternating electrical current generates a proportional, fluctuating magnetic field around itself.
Right. Physics.
The CT clamp acts as a secondary coil. That fluctuating magnetic field induces a tiny, safe proportional voltage within the clamp. The relay reads that tiny voltage, passes it through an analog to digital converter, and the microprocessor calculates exactly how many amps, and therefore how many watts, are flowing through that thick wire in real time.
Down to what accuracy?
Down to a 0.1 watt resolution.
That is incredibly elegant. So the relay isn't just a dumb on-off switch. It is a highly accurate power meter constantly reporting telemetry back to the master controller over the LoRa network.
Exactly. And the true intelligence is applied in Dashboard 4, which is the whole home circuit management interface. This is where the homeowner or installer configures the state machine logic for each of those individual relays.
So you tell the relay how to behave.
Yes. SolarBoost utilizes a 1 to 10 priority sliding scale. Critical lifeline circuits, like the kitchen outlets powering the fridge, might be assigned priority 1.
Makes sense.
High-priority lifestyle circuits, like a stove or the living room air conditioner, might be priority 3 or 4. Down at the bottom of the hierarchy, low-priority deferrable loads, like a pool pump or a borehole pump, are assigned priority 8 or 9.
Okay, so the system understands the hierarchy of needs within the house. But the documentation goes further than just a simple numbered list. It details 4 distinct configurable operating modes for every single circuit.
Yes, and understanding these state modes is how you realize how fundamentally this changes the daily operational rhythm of a home. You can assign any relay to one of 4 rigid modes.
What's the first one?
The first is solar only. This is a highly restrictive state. It dictates that the appliance will only be permitted to run if the CT clamps detect that the solar panels are actively generating a surplus of power greater than what the house is currently consuming.
So it will never pull from the grid.
It will never pull from the ESCOM grid, and it will never, under any circumstances, pull power from the battery.
It lives entirely on free excess energy.
Precisely. The second mode is solar plus battery, meaning it prioritizes pulling excess solar, but it is permitted to draw from the lithium battery if a cloud rolls over.
Okay, maybe more flexible.
The third mode is always on, designed for critical circuits that should never be artificially shed unless the battery enters that absolute stage 3 life support emergency. And the fourth is scheduled, which allows for complex time-based gating.
So practically speaking, I look at the deployment examples in the text. The pool pump relay is set to priority 8, and its state mode is locked to solar only.
Right.
So it's noon. The system's CT clamps see the sun is blazing. The solar array is generating 4,000 watts of DC power, but the house is empty and only consuming 1,000 watts.
You have a surplus.
Right. The grid guard does the math, sees a 3,000 watt surplus and says, great, we have excess power, send a LoRa command to close the pool pump relay. The pump turns on.
Exactly.
But the second the heavy thunderstorm rolls over, where the sun dips below the horizon, the solar generation drops to 500 watts. The grid guard instantly registers the deficit and immediately opens the relay, cutting the pool pump off so it doesn't pull from the grid or start draining the battery.
It acts as an invisible logic gate, constantly balancing the available kinetic energy against the assigned priority of the appliances. And the financial models provided note that simply moving a standard 750-watt pool pump to a strict solar-only mode saves the average South African home R340 every single month.
Just by switching modes.
It completely eliminates the insidious scenario where a dumb mechanical timer turns your pool pump on for 4 hours in the middle of the night, racking up expensive grid consumption, or worse, running during a midnight load shedding block and silently stripping the chemical life from your battery.
Okay, I follow the logic for the pool. It's beautiful.
Yeah.
But I'm going to challenge the hierarchy here.
Go for it.
Let's say I'm configuring the system in my own house. I am absolutely going to set my kitchen stove and my oven relays to always on. Because if I come home from work at 6 p.m., I need to cook dinner for my family.
Naturally.
But wait, if the stove is always on, doesn't that completely defeat the rigid battery protection protocols we just spent 10 minutes discussing? If a blackout hits right at 6:00 p.m. and my stove is pulling 3,000 watts, isn't my battery going to get utterly wrecked?
This is exactly why the platform's multi-layered logic architecture is so crucial. The always-on mode tells the master controller, under normal, healthy electrical conditions, do not artificially restrict this appliance based on solar availability or minor grid fluctuations.
Okay, so it leaves it alone.
However, the battery protection system, those core SOC thresholds from Dashboard 5 serve as an absolute mathematical override.
You override.
It is the supreme law of the platform. If you come home and start cooking and the grid unexpectedly drops, your stove will continue to work perfectly off the battery.
Because it's always on.
Right,
Yeah.
until the exact moment your battery telemetry hits that 20% critical SOC threshold. At that millisecond, the survival of the R150,000 battery supersedes your desire to roast a chicken.
Wow.
The RTOS will forcefully step in, override the always-on user preference for the stove, and sever the relay to protect the chemical integrity of the cells.
That is fantastic design. It gives the user the maximum possible comfort and convenience right up until the exact mathematical moment that comfort becomes financially destructive to the physical investment.
Yes,
Then it steps in and plays the bad cop. It shuts you down.
it has to.
Now, we've talked extensively about pool pumps and stoves,
Yeah.
but we cannot move forward without spending significant time on the absolute elephant in the room,
The geyser.
the geyser, the biggest single threat to both the lithium battery bank and the monthly municipal electricity bill.
It cannot be overstated. For anyone looking at their home energy profile, the electric geyser, the hot water cylinder hidden up in your roof, is a massive, energy-hungry beast.
How much power are we talking?
In a typical South African home, heating water consumes between 30% and 40% of the total monthly electrical load.
40%.
The heating element acts essentially as a deliberate, controlled short circuit, drawing massive amperage to generate thermal energy. If you do not actively control the geyser, you are not really controlling your energy system.
And SolarBoost addresses this specific massive thermal load with a dedicated piece of hardware called the Geyser Guard Monitor.
Right.
According to the engineering specs, this is a non-invasive monitor. It doesn't require a plumber to cut into the tank. It straps directly to the inlet and outlet pipes using dual PT1000 sensors. It has its own dedicated analytics interface, Dashboard 1.
It's highly sophisticated.
And the features listed here go way, way beyond just a glorified Wi-Fi timer switch. It mentions solar priority heating logic, thermostat accuracy scoring, and crucially, something called an anode life prediction algorithm.
Yes.
Let's unpack this. How does this system tame the thermal beast, and what on earth is an anode prediction algorithm?
Let's segment this into two massive benefits: the radical energy savings and the physical appliance protection. On the energy consumption side, the geyser guard utilizes the exact same solar priority heating logic we just discussed with the pool pump.
So it hunts for free energy.
Historically, a geyser operates on a simple internal thermostat. The water cools down overnight, and at 3 a.m., the thermostat clicks, and the geyser pulls 3 kilowatts of expensive grid power to heat the water back up while the house is asleep.
Which is incredibly inefficient.
The geyser guard severs that mechanical loop. It tells the geyser to wait. It waits until the solar ray is peaking, typically between 11 a.m. and 2 p.m., and it uses the completely free excess DC solar energy being converted by the inverter to heat the water up to a high set point, say 65 or 70 degrees Celsius.
And then it just holds that heat.
Because modern geysers are highly insulated, wrapped in dense polyurethane foam, that water retains its thermal energy until you actually need it for a shower in the evening or the following morning.
I'm looking at the financial breakdown of this thermal shifting in the ROI models, and the delta is wild. The engineers calculated that a typical 3-kilowatt geyser, running its element for about 3 hours a day, consumes roughly 270 kilowatt hours of energy a month.
That's standard.
Without the SolarBoost platform, assuming an average municipal tariff of R2.78 per unit, that costs the homeowner R750 a month just for the privilege of hot water.
Yeah, it adds up quickly.
But by forcing that heavy heating cycle into the solar peak window, it drops the grid consumption down to an average of just 54 kilowatt hours a month. The municipal cost plummets to R150.
It's a massive drop.
That is a pure top-line saving of R600 a month, or a net of R550, when factoring in some thermodynamic efficiency losses, just from teaming one appliance.
It is the most aggressive return on investment in the entire home ecosystem. The savings from the geyser guard alone pay back the cost of its specific hardware in a matter of months. But the physical appliance protection, the telemetry data it gathers, is where the mechanical engineering really shines.
This is the anode thing.
You asked about the anode life prediction algorithm. We need to look at the physics of hot water and metal tanks. Inside almost every standard high-pressure geyser is a component called a sacrificial anode rod.
Sacrificial rod.
It is a long stick, typically made of magnesium or aluminum, screwed into the tank alongside the heating element.
I've heard plumbers mention it, but what does it actually do?
It manages galvanic corrosion.
Galvanic corrosion. Okay, what is that?
When you have two different metals in physical contact, immersed in an electrolyte and tap water full of dissolved minerals, is a highly effective electrolyte, a tiny galvanic current flows between them. The laws of chemistry dictate that the less noble metal, the one higher on the galvanic series, will act as the anode and surrender its electrons to the more noble metal, the cathode.
So one metal eats the other?
Basically, the steel walls of the geyser tank are the cathode. The magnesium rod is the anode. The magnesium rod is placed in there specifically to corrode, to dissolve, instead of the steel tank.
Yeah.
It literally sacrifices its own mass to protect the structural integrity of the cylinder.
Okay, so it slowly dissolves over time to stop the tank from rusting.
Exactly. But it is a finite resource. Over a period of 2 to 5 years, depending on the local water hardness, that magnesium rod completely dissolves away to a bare wire core.
And then what happens?
Once the anode material is depleted, the galvanic protection stops. The electrolyte water immediately begins attacking the steel walls of the geyser itself. The steel oxidizes, it rusts through, the structural integrity fails under pressure, the geyser bursts.
Oh no.
Ruins your plasterboard ceiling, floods your laminate floors, and results in a massive traumatic insurance claim.
What's that?
The historical problem has always been that you cannot see the anode rod. It is sealed inside a steel tank in a dark roof space. You have zero idea when it is fully dissolved until the catastrophic failure actually occurs.
Unless you have an algorithm measuring the system. How does strapping sensors to the pipes tell you what's happening to a rod of magnesium inside the tank?
This is where the dual PT1000 sensors come into play. A PT1000 is an incredibly precise platinum resistance thermometer. As the temperature changes, the electrical resistance of the platinum changes in a highly predictable, linear fashion. The geyser guard straps one sensor to the cold inlet and one to the hot outlet. It continuously feeds this high-resolution thermal data into the ESP32. Now, as the anode rod degrades, the internal physical environment of the tank subtly changes. Mineral scaling builds up differently. The heat dissipation curves, the rate at which the water heats up and cools down, begin to shift microscopically over months.
It's reading the thermal signature of the rust, essentially.
By feeding that longitudinal thermal data, combined with tracked usage patterns and regional water chemistry models, into a machine learning algorithm, the grid guard can calculate the hidden corrosion rate.
That is wild.
Dashboard 1 literally gives you a digital readout. Anode life, 15%. Replacement due in 3 months.
This is staggering to me. We treat the geyser like a dumb giant kettle hidden up in the ceiling. We never think about it until hot water stops coming out of the shower head or the ceiling collapses into the hallway.
It's totally reactive.
But this hardware and software integration is doing two incredibly sophisticated things. First, by only heating it when the solar array is peaking, the system is effectively turning the geyser into a massive, free thermal battery.
Yes.
It stores the sun's kinetic energy as thermal energy in the form of hot water, which means the actual lithium battery in your garage doesn't have to waste its precious chemical cycles heating water at night.
It offloads the work.
And second, it is giving you a real-time digital X-ray of the geyser's physical health, telling you exactly when to spend R500 on a new magnesium rod to prevent a R20,000 plumbing disaster.
It fundamentally shifts the concept of home maintenance from reactive trauma to proactive data-driven asset management. You aren't waiting for a catastrophe to flood your house. You are managing a physical asset based on precise telemetry.
Which saves so much money in the long run.
The engineering documentation notes that maintaining the anode extends the physical lifespan of the geyser cylinder by 3 to 5 years, which again is a massive avoidance of future capital expenditure.
All right, let's zoom out for a moment. We've looked at the isolated microcomponents. We've analyzed the ESP32 grid guard, detecting the 49.8 Hz drop in the physical AC wave. We've dissected the 3-stage battery triage protocol. We've looked at the smart relays and CT clamps, acting as an intelligent logic gate network.
We've covered a lot of ground.
And we've seen how the geyser guard acts as both a thermal battery and a diagnostic X-ray machine. Now let's synthesize all of this. Let's look at the daily life upgraded and, more importantly, the hard financial return on investment. Because building out an industrial-grade sensor network in a residential home sounds incredibly expensive.
There is an upfront capital cost, certainly, but this is where Dashboard 3, the Smart Automations engine, and Dashboard 7, the Savings and ROI Analytics interface, prove the economic model. The SolarBoost system isn't just an emergency airbag that only deploys during load shedding.
It's working every day.
It's a daily financial optimization engine. Let's examine a specific, highly lucrative automation they call the peak tariff saver.
I saw that in the models. Walk us through a day in the life of this specific automation algorithm.
In South Africa, Eskom and an increasing number of municipalities are shifting to time-of-use tariffs. This means the cost of electricity is not static. It fluctuates based on national demand.
Okay, so it's more expensive when everyone is using it.
During peak hours, typically 6:00 p.m. to 9:00 p.m. when everyone gets home, turns on ovens, and runs heaters. Electricity is incredibly expensive, often surging to around R4.20 per kilowatt hour.
Wow.
Off-peak power late at night might drop to just R1.95. The peak tariff saver automation allows the grid guard to perform automated energy arbitrage.
Arbitrage like trading stocks.
Exactly. The logic tells the system at exactly 6:00 p.m. physically actuate the relays to disconnect the heavy kitchen and living room circuits from the municipal grid. Force those circuits to run entirely off the lithium battery power that we stored up for free from the sun earlier today.
Oh, that is sneaky. I love it.
For those 3 highly expensive hours, your heaviest consumption is completely shielded from the R4.20 peak rate. Then, at 9 p.m., when the tariff schedule drops back to standard or off-peak rates, the grid guard releases the relays and reconnects those circuits to the grid if the battery needs to be preserved.
It's literally automated stock trading, but with electricity. Buy low, or generate for free, and consume when the grid is trying to sell high.
It's pure optimization.
Okay, let's look at the hard financial numbers from the executive summary of the models, because the engineers are making some very bold, aggressive claims here. The document outlines a typical South African home installation profile. The total initial investment for the hardware, including the GridGuard master controller, the GeyserGuard module, 6 industrial smart relays, and professional electrician installation, is quoted at R$18,500.
Okay.
They claim an average monthly savings of R$1,425. They calculate a payback period of just 9 months, and the total cash saved over a 24-month period is projected at R$42,735, resulting in a net ROI of 231%.
Those are big numbers.
I have to play the skeptic here. A 231% return on investment in 2 years sounds entirely fabricated. It sounds like a late-night infomercial promising impossible wealth. Let's really audit these numbers. Where exactly is that R$1,425 actually coming from every single month?
It is entirely fair to view a 200+% ROI with intense skepticism, but the financial models provided are transparently broken down line by line. Let's stack the math up, using the mechanisms we just spent the last half hour explaining.
Okay, show me the receipts.
First, we have the geyser optimization. By shifting the heavy heating cycle to the solar peak window and vastly reducing grid consumption based on the PT1000 thermal data, we established a proven net saving of R$550 per month.
Okay, the thermal battery concept. R$550 is in the bank.
Second, the battery protection mechanism. By ruthlessly enforcing the 3-stage protocol, preventing those deep discharge microfractures in the anode, and extending the R150,000 battery's viable life from 5 to 10 years, we calculated a monthly avoided depreciation cost of R$12,250. However, if you look closely at the SolarBoost ROI model, they are actually being highly conservative. They only claim R$375 a month in their direct savings tally for the battery.
Wait, why so low?
This is likely accounting strictly for the avoidance of emergency grid charging at high peak rates when a totally depleted battery desperately needs to recover chemical stability after a brutal load-shedding block.
That is extremely conservative. They are leaving almost 1,000 Rand of depreciation savings off the headline number to be safe. But fine, we will use their numbers. R$550 for the geyser, plus R$375 for direct battery protection charging avoidance. We are sitting at R$925.
Third is the circuit optimization and relay management. By putting the pool pump, borehole pump, and other 9 essential hydro appliances on strict solar-only logic gates, eliminating midnight timer runs and grid usage. The telemetry data proves an average net saving of R$300 per month.
That brings us up to R$1,225.
And finally, that peak tariff avoidance arbitrage we just discussed. By programmatically shifting daily consumption away from the punitive R4.20 rate block and into the free solar or R1.95 off-peak blocks, their models estimate a highly conservative saving of R$200 per month.
R$550 plus R$375 plus R$300 plus R$200. There it is, exactly R$1,425 a month.
The math works.
When you break it down system by system, relay by relay, appliance by appliance, the math undeniably holds up. You aren't finding one massive magical solution. You are finding a dozen different thermodynamic inefficiencies and bleeding financial wounds in the home's daily energy profile, and the SolarBoost system is applying an automated tourniquet to all of them simultaneously.
And if you project that forward, factoring in Eskom's historically inevitable compound tariff increases and 15% annually might be too low given recent trajectories. The projected aggregate savings over a 10-year lifespan are calculated at R$215,000.
That is life-changing money.
It's not just about spending less municipal money today. It's about the profound psychological peace of mind. Knowing you have a localized, high-speed computational system actively fighting the tariff hikes and load-shedding degradation on your behalf 247 without you ever having to open an app.
Which perfectly transitions us into the final major topic from the technical stack.
Yeah.
Because it is fantastic that the hardware and software work beautifully today on day one of installation.
Sure.
But how does a system this complex ensure it keeps working tomorrow, next year, and in 5 years? And looking even broader, what is the macro impact when tens of thousands of homes start deploying this intelligence layer?
To understand the longevity and maintenance of the platform, we have to look at Dashboard 6, the Alerts and Maintenance Center, and critically, Dashboard 8, the Secure Installer Portal.
The installer portal.
SolarBoost fundamentally alters the relationship between the homeowner and the solar installation company. Historically, an installer only hears from a customer when something is catastrophically broken.
My house is dark. Come fix it.
Exactly. The installer rolls a truck, drives an hour through traffic, spends an hour with a multimeter diagnosing the board, only to realize a single relay just needed a software reset or a battery reset. BMS needed a manual calibration. It is incredibly inefficient and expensive for everyone involved.
But with Dashboard 8, the installer portal, the paradigm shifts entirely.
Completely.
The installer has secure, PIN-protected remote access to a live, high-resolution diagnostic stream. They can sit in their office and see the exact millivolt readings of the grid, the thermal temperatures of the battery cells, the RF signal strength of every LoRa node in the house.
All in real time.
The release notes state they can execute complex, one-click calibrations over the internet. The business models project this reduces expensive installer on-site truck rolls by 50%.
Exactly. The system generates highly actionable, data-rich alerts. It doesn't just throw a generic error 404 on a screen.
Nobody likes those.
It sends a push notification saying, geyser and node life critical, 5%. Galvanic protection failing. Replacement highly recommended, with a direct hyperlink right there in the alert to schedule maintenance with the installer.
It's so proactive.
Or the system detects a logic flaw and announces, firmware update available, improved ESP32 RTOS energy optimization, which the grid guard downloads over the air completely autonomously without a technician ever setting foot on the property.
I'm going to bring back my ship's captain metaphor, but modify it slightly.
Let's hear it.
It's like having an invisible, highly trained chief engineer living inside your distribution board. It runs the ship's engines at maximum efficiency. It texts you when a part is showing microscopic signs of fatigue. It literally calls its own mechanic via the installer portal to run diagnostics before a minor issue becomes a critical hull breach.
That's a perfect way to visualize it.
And meanwhile, while it's doing all this self-maintenance, it's doing incredible things for the broader environment.
Yes, the environmental impact metrics in the datasheets are highly compelling. By relentlessly optimizing loads and increasing an average home's solar self-sufficiency from a baseline of roughly 45% up to a highly efficient 78%, an average SolarBoost-equipped home actively offsets 3,995 kilograms of carbon dioxide emissions per year.
Almost 4 tons.
That is the tangible carbon capture equivalent of physically planting 190 mature trees per home every single year.
190 virtual trees planted in your backyard annually, simply by allowing an algorithm to optimize exactly when your pool pump and geyser consume energy. That is a massive, tangible macro impact.
It's huge.
And it looks like PowerPulse Innovations, the engineers behind this, aren't stopping at just optimizing individual homes. The final section of the documentation, the 2025-2027 Strategic Roadmap, outlines some truly wild future ecosystems.
Oh, the roadmap is ambitious.
I see notes on EV charger integration, community energy sharing. Unpack this for us. Where is this technology actually heading?
The roadmap reveals their ultimate architectural ambition. Once you have the grid guard controller successfully deployed in tens of thousands of homes across a city, you no longer just have a collection of isolated smart homes. You have laid the physical hardware foundation for a massive distributed energy network.
A network.
They are engineering peer-to-peer energy sharing protocols, where you could theoretically utilize the municipal grid infrastructure to sell your excess noon solar power directly to your neighbor who doesn't have panels.
Selling power to your neighbor? That's incredible.
But the absolute biggest leap, the concept that changes national infrastructure, is the integration with ESCOM and local municipalities to create a virtual power plant, or VPP.
Okay, we need to spend some time here. Define a virtual power plant in deep detail. How does my house become a power plant?
A virtual power plant is a cloud-based, centralized control system that aggregates the capacities of thousands of heterogeneous distributed energy resources.
In plain English, please.
Right. In plain English, instead of the national utility spending 100 billion rand in 10 years building a massive new coal or open-cycle gas turbine power station, just to handle the massive spike in demand that happens every evening between 6 p.m. and 8 p.m., the utility could partner with a software platform like SolarBoost.
Okay.
During a critical grid crisis, when the 50 Hz frequency starts to drag dangerously low, ESCOM doesn't initiate rolling blackouts. Instead, the VPP sends a secure, instantaneous, encrypted signal to the master controllers in 50,000 connected homes.
And what do they do?
The grid guards instantly actuate the relays, and 50,000 3-kilowatt geysers and pool pumps turn off simultaneously for exactly 20 minutes.
Wow. The system artificially and instantaneously removes hundreds of megawatts of strain from the national grid.
Precisely. It is a highly coordinated algorithmic demand-side response. It instantly stabilizes the national grid, preventing the turbines from bogging down, entirely avoiding the need for localized load shedding.
That is brilliant.
And the financial model here is that the utility actually pays for this service. The homeowner receives a monthly microtransaction, say R300 or R400, credited to their account simply for allowing the VPP to temporarily pause their pool pump during a national crisis. It is the ultimate democratization of grid stability.
Which brings us to the end of our deep dive today. Let's trace the massive arc we've just traveled. We began by looking at the stark reality of a passive, deeply vulnerable solar setup. That R150,000 sports car left idling in the driveway with the keys in the ignition, completely at the mercy of sudden load shedding and the silent chemical destruction of deep battery discharges.
And we've unpacked the microarchitecture of how adding the SolarBoost intelligence layer transforms that vulnerable sitting duck into an active, mathematically optimized
The
fortress.
fortress, yes.
It provides supreme automated protection for the lithium cells via that ruthless three-stage triage protocol, triggered instantaneously by the ESP32 detecting a microdrop to 49.8 hertz on the AC sine wave.
It physically protects massive appliances through thermodynamic innovations, like the PT1000 anode prediction algorithm. It entirely eliminates the deep cognitive load of manual circuit toggling. And it backs every single action up with a mathematically proven, aggressively verified 9-month financial payback period.
It fundamentally rewrites how you interact with and pay for your home's kinetic energy.
But I want to leave you with a final provocative thought to mull over. Building directly on that massive virtual power plant concept we just explored, millions of South Africans bought these expensive solar and battery systems specifically to escape the trauma of load shedding.
That's the whole point.
We install localized intelligence platforms like SolarBoost specifically protect those batteries from load shedding. But if platforms like this continue to scale, if they successfully network 50,000, 100,000, or 500,000 homes into a colossal virtual power plant that can actively, instantly, and algorithmically stabilize the national grid during peak demand,
Yeah.
will the very concept of load shedding eventually become completely obsolete?
It's a huge question.
Think about the profound socioeconomic shift. Will the highly localized intelligence system you bought selfishly just to protect your own home's battery chemistry ultimately end up being the exact decentralized network technology that permanently protects the entire country's power grid?
It is a truly fascinating paradox of scale. The ultimate hyper-localized defense mechanism for the individual homeowner organically scales up to become the ultimate stabilizing mechanism for the entire national collective.
It really is a stunning piece of engineering. Thank you for joining us as we crack the code on the SolarBoost Complete Home Energy Management Platform. Look at your own home's energy footprint differently today. Think about the thermal mass of that geyser. Think about those invisible lithium ions degrading during a blackout. Until next time, keep exploring the data, keep questioning the infrastructure, and keep diving deep.